All right, students, this is a copy of the notes that we will be covering together in class on Wednesday, September the 18th. Thought I'd go ahead and do a recording of it and post it just in case anybody was wanting to get ahead, but we will be discussing these notes in class on Wednesday. Today's topic is amplitude changes. All right, our objective today will be the student will discover the effects of amplitude changes upon parent functions and their equations. Again, the notes are for September the 18th, so please date them. As always, press pause anytime you need to, and then hit play whenever you're ready to move forward. All right, today we will continue looking at changes that can be made to the parent functions and see what effect they have on the graphs. We've already discussed vertical shifts and horizontal shifts, and we saw that those happen by way of values, constants being added either to the equation itself or to the independent variable itself. And today we're going to have a look at what we call amplitude change. Now, an amplitude change can alter both the height of a function as far as its range values are concerned, as well as inverting it in some manner. Now, as you're going to see, sometimes the inversion, as I refer to it there, it can be a little bit tricky depending on what type of a function you're looking at, but we'll get into all of that. Okay. Now, in an equation, what we're looking for is if we have an amplitude change, it is going to be found by looking for a coefficient that is influencing the independent variable. And in an equation, basically, this is what we're talking about. Y, or f of x, equals, and then wherever your independent variable is, there is a coefficient of some kind, whole numbers, decimal points, fractions, positives, negatives, all of that stuff is having an effect on the independent value x. All right, so let's look at some changes to the parent functions that we have discussed. Okay, we've been starting off with the parabola, so we'll start off again with the parabola. Okay, we can see from the left-hand equation there, that is the parent quadratic. F of x equals x squared. Nothing added or subtracted to x or to the equation, and definitely no coefficient of x, and it's positive. Okay, but when we look at the other two, look at what we see. The one in the middle, f of x equals 2 of x squared. And the one on the right-hand side, 1/2 of x squared. When we change the coefficient in front of the independent variable, what that is going to do is it's either going to speed up the graph, causing it to go off to infinity faster, or it's going to slow down the graph, causing it to take longer to go off to infinity. Okay, so here is what we might be looking at. Obviously, the left-hand function is the parent function. Opens up at its standard speed, pointing upwards, and it's rising at its regular pace. The one in the middle, y equals 2x squared. That 2 is actually causing an increase in the speed in the range. Okay, and it's kind of easy to think about when you think about values plugging into this function machine, y equals 2x squared. When we plug in x values, the same x values we plug in on the left, we can plug in the middle, but because they're being multiplied by 2 after they're being squared, that's causing the range to be twice as high up as it would have been. So our parabola becomes more narrow. And the reverse argument happens over there on the right side. F equals 1/2 of x squared. When we plug in the same x values that we plugged in everywhere else on the screen, then they get multiplied by 1/2 after they were squared, and that's going to cause the y values to be half as big as they would have been compared to the parent function. So our graph becomes wider because it's not rising as fast as it used to. Okay. Now the basic rule here is the value of the coefficient tells us to what degree the speed has been magnified. With parent functions, the standard typical speed is 1. Every coefficient we've seen with parent functions has been a 1. Y equals 1x squared. Y equals 1y cubed. Y equals 1 logarithm of x. Okay, but when you start changing that 1 into a number smaller than 1, by smaller than 1, I mean between 0 and 1, okay, that's going to cause the graph to rise slower than it would have. And if you take that 1 and start making it bigger numbers, 2, 3, 19 and a half, stuff like that, the bigger it goes, the faster the graph is going to rise. Okay, now another thing that can happen with the coefficient of our independent variable is that it might flip to a negative. Okay, now when this happens, it's going to be a little bit tricky. This is probably going to be the hardest part of working with the equations for most of you, because you're really going to have to slow your brain down and think about this. Okay, so let's take a look at a couple of functions for starters. Okay, we have our parent quadratic function on the left side, f of x equals x squared, and on the right side, not a parent function because it's not a positive 1 coefficient. Now it's a negative 1 coefficient. Let's take a look at what that did to the graph. Okay. Flipped it upside down. Okay. But there are other situations where changing the coefficient from a positive value to a negative value doesn't turn the graph upside down, it actually swings it around backwards. Okay, so let's look at the parent function, y equals logarithm of x, and compare it to y equals the logarithm of negative x. Let's look and see what that did. Okay, so you can see it doesn't have the same effect. The same change made to certain equations does not have the same effect on other equations. And we're not even done looking at the differences yet. Okay, on other ones, there may be no change made to the equation or to the graph because the change to the equation has been made. Let's look at these three equations. Let's examine the differences of these. Okay, you have the parent absolute value function on the left, y equals square root of x. In the middle, we have y equals, I'm sorry, I said square root, I'm in absolute value. Y equals absolute value of x on the left. Y equals the absolute value of negative x in the center. And y equals the negative of the square root of x over on the right-hand side. Okay, so let's think about this for just a moment. Okay, the positioning of the negative on those final two, the middle one and the right-hand side, is different. Okay, what is that going to change? Well, let's remember, what is it that absolute value bars do? Okay, absolute value measures a distance from 0 on the number line to wherever this thing is, whatever's inside of the absolute value bars, where it is on the number line. How far is that away from 0? That's a distance. Distance is always going to be positive. So on this equation in the middle that says the f of x equals the absolute value of negative x, well, when that negative x comes out of those absolute value bars, it's not going to be negative anymore. It's going to be positive because distance is always positive, and absolute value is the same thing as measuring a distance. Okay, so is there going to be any difference between the graph on the left side and the graph in the center? Okay, once the absolute value bars are removed, they will both say y equals x, or f of x equals x in both cases. The left graph and the center graph are going to be identical. What about the one on the right side? Okay, we have absolute value bars wrapped around x, okay, but once the absolute value bars come off of that x, it's still an x, but the negative sign is out there waiting for it. Okay, so when the x comes out, it's going to become negative because of the negative outside of the absolute value bars, and that's actually going to turn that graph upside down. Okay, now what we need to do is we need to kind of figure out a little bit of a system here. How are we going to determine when graphs are going to be flipped upside down or when they're going to be flipped sideways and stuff like that? And I wish I had a great way to explain it to you. Okay, but I really don't. The only thing that's going to save you here is really thinking about what's going on. So all I can say is, in short, you have to consider each function and how a sign change in the equation would affect each graph. Okay? And much of that will be deciding if a negative has just changed the independent variable x, or if it essentially changed the entire equation f of x. And we'll look at this in greater detail here when we get to these examples. Okay. Now the same is going to be true for all of our functions. Okay. We haven't seen all the functions. We don't know how the negatives and things like that are going to affect them. But let's take a look. Okay. What type of a graph do you have on the left-hand side? This one is cubic. Okay. So let's start thinking about this here. What is it that a cubic function is supposed to do? Okay, it is supposed to pass through the origin, which it is. Okay, and if you remember the cubic function, okay, the parent cubic function, or think about the points that go into the cubic function, okay, we should have points like 1 comma 1, 2 comma 8, 3 comma 27. Okay, because when you plug in those x values, those inputs, the outputs in the range are getting very big very quickly because they're being cubed. Okay, but look at the points that we have here. We seem to have 1, 1. Okay, but by the time you move over to 2 on the number line, the graph is already, looks like it's trying to shoot off to infinity already. Okay, this graph is moving faster on the range than we would like it to, or than the parent function would suggest. So what does that mean about the equation? It means that we're going to have a larger coefficient in front of our independent variable x. So we should be looking for maybe y equals 2x cubed, or maybe 3x cubed, a bigger coefficient because the graph is going to infinity faster. The one in the middle, what type of a function is that? Okay, it looks like an absolute value function. It has the same basic mannerisms. It's linear, and it has that deflection point inside of it. Okay, but we're accustomed to our absolute value functions going upward. Okay, so it seems like we're going to have a sign change somewhere. What we need to do is figure out where that sign change will be. And another thing we need to figure out is whether this graph is moving at the speed that we think it should be, or whether it's been sped up or slowed down. Okay, well, the absolute value function, okay, the parent function, when you plug in 1 for an x, you get 1 for a y. When you plug in 2 for an x, you get 2 for a y, 3 for x, 3 for y. When you look at the points where this line is connecting, it looks like at positive 1, we're down at about 1/2. At positive 2, we're down about 1. So it appears that this graph is moving about half as fast as the parent function would have liked. So we're probably looking at a coefficient somewhere around 1/2. Okay. Now the negative. Okay. What has become negative? Okay. Did the graph's x values reverse themselves, like the positive x-axis went to the negative x-axis and the negative x went to the positive x? No, that would have just spun the graph around. So it's not the x value that changed. However, the graph did go upside down. Okay, so what's the difference between being above the x-axis and being below the y-axis? The sign of y. Okay, above the axis, that's positive y. Below the axis, that's negative y. So we're going to have to change the sign of the entire equation, and we'll take a look at how that actually gets done here in just a second. On the third graph down there, okay, what type of a function is this? Well, the positioning and the kind of the nature of it looks very similar to the exponential function. But as you remember, the exponential function is supposed to come from the negative x-axis through positive 1, get into the first quadrant, and then head off to infinity. This one seems to be spun around. Okay, it's coming from the positive x-axis through the y-axis at positive 1, and then shooting up into the second quadrant. Okay, but it is crossing where it's supposed to. It is in quadrants 1 and 2 like it's supposed to be, but it looks like it's been spun around. So we need to think, okay, that's probably a sign change. So what actually had to change to spin that graph around? Okay, if we switch the axes, the x-axis around, that would spin the the graph around. So what we want is we want the positive x-axis to become negative, and we want the negative x-axis to become positive. So that's most likely a sign change on x itself. Okay, so let's take a look and see how we did. Okay. On the left-hand side, we said that the cubic function was moving faster than it should, so we should expect a larger coefficient in front of x. And there it is. In the middle, we said that we should be expecting an absolute value function, that our absolute value function was moving slower than it should have been. Okay, and so we have a smaller coefficient for x, but we also said it was upside down. Okay, that instead of being on the positive y-axis, it's on the negative y-axis. So we had to change the sign of the entire equation. So that's how come there is a negative sign outside of the absolute value bars. Once 1/2 x comes out of the bars, the negative sign is going to be waiting for it, and that's going to flip the graph over. And we said on the exponential function down there, we said that it was pretty much all okay, except for the fact that we felt like it was spun around and the x values needed to change direction. Positive x needed to become negative and negative x needed to become positive. So that's how come you have the little negative sign on your exponent of x. Okay, two more let's have a look at. On the left-hand side, what type of a graph is this? This one appears to be something similar to the logarithmic function, comes up from negative infinity, but our typical logarithmic function should cross the positive x-axis and then head off to infinity on the x-axis. This one is going the opposite direction. It's on the left side, the negative side of the y-axis. Okay, but it still comes through the 1 value like it's supposed to. It's just coming through -1, and then it's heading off to negative infinity. So it seems once again that this graph has been rotated around side to side. Okay, so again, when we write the equation, we're going to be looking for a way to change the x value sign. We want the x-axis to positive x to be negative and the negative x to be positive. So we're going to have to switch the sign of x when we answer. And the final graph, okay, what type of a graph is that? That one is the square root function. This one doesn't look like it's behaving the way that it's supposed to. Okay, when you plug values into the square root function, okay, like if you go to 1 on the x-axis, the parent function would tell you you're at 1 on the y-axis as well. Okay, when you go out to 4 on the x-axis, well, the square root of 4 would be 2. Clearly, this graph is going up higher than that. This one has a change to its amplitude value. Okay, matter of fact, it looks like at 1 on the x-axis, we're closer up to 2 on the y-axis, and at 4 on the x-axis, we're closer up to 4 on the y-axis. So I believe that this one has been doubled in its amplitude, so we should probably be looking for a coefficient of 2 on our answer. Let's take a look. Okay, yes, exactly as we said, that the logarithm on the left-hand graph, we had to reverse the x-axis because it is heading the wrong direction on the x-axis. So we changed the sign to match the graph, and then on the on the other, we have the graph is moving twice as fast on the y-axis as we expect, so the coefficient of x should be doubled. Okay, now the same thing's going to be true that has been true for the last couple of days. We're going to have to reverse this process. Okay, not only are we going to be looking at the graphs to try to figure out the equations, we're also going to be getting equations to try to figure out the graphs. So let's have a look. Obviously, first one, square root of x. So we're going to square root function. Okay, what's going to be different about this one? The x value has had its sign reversed. Okay, if that's the case, instead of leaving the origin and heading off into quadrant 1 like it's supposed to, we're going to leave the origin following the y-axis, so we're going to head into quadrant 2. We'll take a look at the graph here in a moment. The middle one, obviously, this one is exponential. Okay, but what has been changed about it? It is now negative. Okay, so, but what is negative? Did the sign of x get reversed, or did the entire side of the equation get reversed? Okay, it's the entire side of the equation. So when that happens, that is going to cause our graph to change its y values. So instead of coming out of the second quadrant, crossing the positive y-axis and heading off to infinity in quadrant 1. We should probably expect this one to be coming in quadrant 3 along the y-axis, crossing the along the negative x-axis, crossing the negative y-axis, and then heading off to negative infinity in quadrant 4. We'll look at it here in a second. And the final one that's showing now is obviously cubic. Okay, and once again, it's not the parent function. It has a sign change. Okay, but what does that actually change? Okay, we need to make a decision here. Is the value of x being changed, or is the entire side of the equation being changed? Okay. People are going to have different opinions on this right off the bat, but I'll tell you that the correct answer is it is not x that got changed. Okay, because technically what we are looking at right there is a negative sign of x being cubed. Okay, so x can be cubed just like it is, but the negative is waiting for the x value to be cubed before the negative sign actually applies. So we should expect that this function is getting all of its x values, or it's getting its y values reversed. Okay, and that is going to cause the graph to flip upside down. So instead of coming upward in quadrant 3, turning through the origin and going up into quadrant 1, it should be coming down through quadrant 2, turning through the origin, heading down to a negative infinity through quadrant 4. And there are the graphs. Let's look at them real quick, see if we got them right. Okay, on the absolute or the square root function, yes, changing the sign of x caused it to leave the origin and head the wrong direction. Okay, on the exponential one in the middle, again, changing the sign of the entire right side of the equation caused it to the y value to be reversed. So instead of being all above the x-axis, it's all below the x-axis. And on the cubic function, yes, the value of y was switched, so the graph was turned upside down. Okay, a couple more here. Logarithmic. Okay, logarithm equation is supposed to come up along the positive side of the negative y-axis, okay, and then turn through positive 1 on the x-axis, head off to infinity in quadrant 1. Okay, but the sign has been reversed. So what has been reversed? Is it the x values that are reversed, or is it the entire side of the equation? The entire side of the equation is reversed. That's causing the y values to flip. So instead of it coming up along the x-axis and then turning into quadrant 1 and heading off to infinity, now it should be coming down the y-axis, crossing positive 1 on the x-axis, heading off to infinity in quadrant 4. Okay, and finally, the last function there, absolute value of negative 1/3 of x. Now, obviously, we got a coefficient change there on x. Will that speed the graph up, send it to infinity faster, or will it slow it down, sending it to infinity slower? 1/3 is smaller than 1. That's going to slow it down. So this graph is not going to be going as fast towards infinity as it normally would. What is the negative change? Okay, this one's kind of a little tricky spot right here. Yes, x has changed signs, but what are the absolute value bars going to do with that negative sign when 1/3 of x tries to come out? Okay, the absolute value bars are going to steal that negative sign because absolute value is, in essence, a distance. An absolute value is not going to let a distance be positive. So we should expect that the graph is still going to be upward instead of flipped, because we did get to steal that sign from there because the absolute value bars. Okay, so those are the two graphs that I did discuss. It looks like we described them and got them right. Okay, this is going to take a little bit of getting used to. It's going to take some practice, and we need to be doing a little bit better job on our assignments. It seems like a lot of people are just kind of scribbling in a bunch of random answers at the last moment, and the grades are looking pretty bad with that kind of an effort. Okay, this is not nearly as easy to understand as the vertical change, the vertical shifts and the phase shifts. So please pay careful attention to these notes, reread them, rewatch them, do whatever you need to do. But this is going to be critical to to your success on working with changes to the parent functions.